On the 19th of July, 2024, 8.5 million computers worldwide suddenly collapsed into a wall of blue screens, marking the largest IT outage in history. This unprecedented catastrophe was not caused by a sophisticated hacker or a malicious cyber attack, but by a routine 40-kilobyte software update from the security firm CrowdStrike. The scale of the disruption was immediate and global, affecting airports, hospitals, banks, and emergency services, effectively freezing the digital infrastructure of the modern world. To understand how a tiny file could cause such massive damage, we must look at how CrowdStrike's Falcon software operates deep within the architecture of Windows. Most applications on your computer, like your web browser or games, run in what engineers call user space, where they are isolated from critical system functions. If a standard app crashes, Windows simply closes the program and allows the rest of the system to continue running without any major interruption to the user. However, CrowdStrike's Falcon is different. It is designed to stop sophisticated threats, which requires it to live in the kernel, the engine room of the OS. The kernel is the core of the operating system, holding direct control over your computer's memory and hardware, making it the most powerful and sensitive layer. This deep integration grants Falcon the authority to intercept malicious code before it can do harm, providing a high level of security against nation-state attacks. But this power comes with a significant trade-off, because in the kernel, there is no safety net to catch a program if it suddenly fails. If code running at this level encounters an error, the operating system cannot isolate the problem, forcing the entire machine to trigger an emergency stop. This emergency stop is the infamous blue screen of death, a protective mechanism that halts all operations to prevent further damage to the system's core integrity. To stay ahead of new cyber threats, CrowdStrike constantly updates its defenses by pushing small instruction files, which they refer to as channel files. Think of these channel files as new wanted posters for the security guard at the door, providing updated descriptions of what the software should look for. These files are designed to be lightweight and are often pushed silently to millions of machines simultaneously, sometimes several times throughout a single day. On that July morning, the update labeled Channel File 291 was distributed globally, carrying a hidden flaw that would soon trigger a worldwide digital collapse. Initial reports suggested the Falcon sensor was programmed to read a list of exactly 20 inputs, which we can visualize as a row of 20 numbered chairs in memory. The flawed update file arrived and issued a command to the sensor, instructing it to check the data located in chair number 21. Because there was no 21st chair, the program reached past the end of its own list into memory space that it did not actually own. It grabbed whatever random data happened to be sitting in that memory location and attempted to treat that garbage as a legitimate system instruction. Engineers call this an out-of-bounds read, a common programming mistake that usually results in a simple crash for a standard isolated application. But because this occurred within the kernel, the mistake did not just close a single program, it detonated the entire operating system on every machine. 20 chairs, one simple order to sit in the 21st, and 8.5 million computers hit the floor in a matter of minutes. This raises the most troubling question of all. How did a flaw this simple pass through the company's internal quality control and validation procedures? CrowdStrike utilized an automated inspector designed to check these channel files for errors, but the inspector itself contained a critical, overlooked bug. The inspector assumed that the 21st slot would always be safe to access, so it incorrectly stamped the broken file as clean and ready for release. Because these channel files were treated as harmless data rather than executable code, they bypassed the slow, careful testing that actual software updates receive. There was no small test group to catch the error and no gradual rollout to limit the damage. The update was pushed to everyone at once. One button press sent the update to every machine on Earth at the exact same minute, creating the fastest, most fragile deployment pipeline in history. 62 minutes later, CrowdStrike realized the scope of the disaster and pulled the file, but for millions of machines, the damage was already done. The affected computers were trapped in a boot loop, meaning they were too broken to start up, and therefore too broken to receive the automated fix. The cure existed in the cloud, but the patients were offline and unable to reach it, forcing IT teams to resort to a manual, medieval repair process. A human being had to physically walk to each affected machine, boot it into safe mode, and manually delete the poisoned file from the system folders. This process had to be repeated for every single computer, leading to exhausted IT teams working through the night across every global time zone. The situation was further complicated by corporate security policies, as companies using disk encryption required a 48-digit recovery key for each machine. Some organizations had stored these keys on servers that were themselves showing a blue screen, leaving them locked out of their own recovery tools. The financial impact was staggering, with Fortune 500 companies alone losing an estimated $5 billion due to the massive operational downtime. One major airline, Delta, canceled thousands of flights and eventually took the matter to court, seeking roughly $500 million in damages. It took about 10 days of intense, around-the-clock labor just to get 99% of the affected sensors back online and functioning properly. The uncomfortable truth left behind by this story is that July 19th was not really about one bad file, as software bugs occur every single day. The outage happened because the modern world runs as a monoculture, relying on one operating system and a handful of security vendors for protection. All of these systems are wired for instant, global, and automatic updates, which is a design that is beautifully efficient but also efficiently fragile. The same high-speed pipeline that pushes critical security protection to millions of machines in minutes also pushes a single mistake to all of them. This fundamental design has not changed, which means that somewhere right now, another routine update is waiting for its turn to stop the world. If you think this was a one-off event, it is important to remember that this is not even the first time such a failure has occurred. Years earlier, a single mistyped command inside Amazon's infrastructure took down a significant portion of the internet in a matter of minutes. These events serve as a stark reminder of how interconnected and vulnerable our digital infrastructure has become in the pursuit of constant, automated updates. The reliance on centralized security firms creates a single point of failure that can turn a minor coding error into a global economic crisis. As we continue to build more complex systems, the challenge of maintaining stability while ensuring rapid security updates will only become more difficult. The CrowdStrike incident highlights the need for better validation, more robust testing, and a move away from absolute, blind trust in automated deployment. We have prioritized speed and convenience, often at the expense of the resilience required to handle the inevitable errors that occur in complex software. The blue screen was a wake-up call for the entire tech industry, forcing a re-evaluation of how we manage the software that runs our lives. While the immediate crisis has passed, the structural risks remain, embedded in the very way our modern computing environments are architected and maintained. Understanding these risks is the first step toward building a more reliable future, where updates can be delivered without threatening the global economy. The story of the 8.5 million crashed computers is a lesson in the fragility of our digital world and the power of small mistakes. It reminds us that even the most sophisticated security systems are still built by humans, and humans are prone to errors in logic and design. As we look ahead, the question remains whether we will learn from this failure or continue to rely on the same fragile, high-speed update pipelines. The next time your computer updates, remember the row of 20 chairs and the invisible danger that could be lurking in the next line of code. The full story of the Amazon outage is on screen now, providing the perfect companion to this investigation into the fragility of our digital age. The catastrophe was not merely a technical glitch, but a failure of the automated validation system designed to catch such errors. CrowdStrike relied on an inspector tool whose primary job was to verify these channel files before they were ever released publicly. However, that inspector contained a critical blind spot. It assumed that the 21st slot in the memory list was always safe. Because of this faulty assumption, the inspector erroneously stamped the broken file as clean, allowing it to pass through the gates. This oversight meant the update bypassed the rigorous manual testing protocols that are typically reserved for full-scale software releases. By treating these channel files as harmless data rather than executable code, the system effectively skipped all necessary safety checks. There was no small test group to catch the error, and no gradual rollout to limit the scope of the potential damage. Instead, a single button press pushed the update to millions of machines across the entire planet at the exact same minute. It was the fastest possible update pipeline, yet it was pointed directly at the most fragile part of the operating system. Within 62 minutes, CrowdStrike realized the error and pulled the file, but for millions of users, it was already far too late. The affected machines were trapped in a vicious cycle, caught in a persistent boot loop that prevented them from functioning correctly. Because the computers were too broken to boot into their normal state, they were also unable to download the necessary remote fix. The digital cure existed on the company's servers, but the patients were effectively locked out, unable to reach the medicine. This forced IT teams into a desperate, manual repair effort that felt more like a return to the medieval age of computing. A human being had to physically walk to each individual machine to intervene, turning a global problem into a local nightmare. They had to boot each system into safe mode, dig deep into the Windows system folders, and manually delete the poisoned file. Then, they had to repeat that exact process again and again for every single computer that had been rendered useless. IT professionals pulled exhausting all-nighters across every time zone, struggling to restore services that the world relies on daily. The situation was made even crueler by security protocols, as companies using disk encryption required a 48-digit recovery key. In many cases, those vital keys were stored on servers that were themselves showing nothing but a blue screen of death. Fortune 500 companies alone suffered an estimated $5 billion in losses, highlighting the sheer scale of the operational collapse. One major airline, Delta, canceled thousands of flights and eventually went to court over roughly $500 million in damages. It took about 10 days of non-stop effort just to get 99% of the sensors back online and fully operational. This entire incident reveals an uncomfortable truth about the digital infrastructure that underpins our modern, interconnected global society. July 19th was not really about one bad file, because software bugs and human errors happen in every industry every day. The true issue is that the modern world runs as a monoculture, relying on one operating system and a few security vendors. Everything is wired for instant, global, and automatic updates, which creates a system that is beautifully efficient but dangerously fragile. The same high-speed architecture that pushes vital protection to millions of machines in minutes also pushes mistakes to all of them. Because this fundamental design has not changed, the risk of a similar catastrophic failure remains baked into our digital foundation. It means that somewhere right now, another routine update is waiting in a queue, potentially ready to stop the world again. If you think this was a one-off event, it is important to remember that it was not even the first time. Years earlier, a single mistyped command inside Amazon took down half of the internet in a matter of mere minutes. That previous incident serves as a perfect companion to this story, illustrating the inherent volatility of our complex digital systems. We have built a world where efficiency is prioritized above all else, often at the expense of necessary, built-in redundancy. The reliance on automated systems means that when things go wrong, they go wrong at a scale that is almost impossible to manage. We must ask ourselves if the speed of these updates is worth the risk of a total, global, system-wide blackout. As we move forward, the challenge will be to find a balance between keeping our systems secure and keeping them stable. Until that balance is found, the fragility of our interconnected world will continue to be a silent, looming threat. The blue screen of death served as a stark reminder that our digital lives are held together by very thin threads. Every update is a gamble, and in this case, the house finally lost, costing the world billions in just one morning. The recovery process was a testament to human persistence, but it also highlighted the limitations of our current repair strategies. We cannot simply rely on manual intervention when the scale of the failure reaches into the millions of devices globally. Moving forward, developers and security firms must rethink how they validate and deploy code to prevent such massive outages. The lesson of July 19th is clear: we need more robust safety nets, even if they slightly slow down our update pipelines. Efficiency is a goal, but stability is a requirement for any system that supports the essential functions of modern society. The reliance on a monoculture makes us vulnerable, and diversifying our digital tools could be a key path toward resilience. We must stop treating software updates as purely data and start recognizing their potential to act as system-level commands. The distinction between data and code is becoming increasingly blurred, and our security models must adapt to this new reality. This story is a warning that our digital world is not as solid as it appears, and it requires constant vigilance. The next time you see an update notification, remember the millions of machines that went dark on that July morning. It is a reminder that even the most sophisticated systems are only as strong as the processes governing their updates. We have created a world that is always on, but we have yet to master the art of keeping it always safe. The cost of this outage was not just financial, it was a loss of trust in the systems we depend on. Rebuilding that trust will require transparency, better testing, and a fundamental shift in how we approach global software deployment. The architecture of our digital world is a marvel, but it is also a house of cards waiting for a gust. We must ensure that the next update brings progress, not a total halt to the functions of our modern civilization. The story of CrowdStrike is a chapter in the history of computing that we should study to avoid repeating mistakes. As we continue to innovate, let us keep the fragility of our infrastructure at the forefront of our engineering efforts. Only by acknowledging these risks can we hope to build a future that is both fast, secure, and truly resilient. The world is watching, and the next update is already being prepared, hopefully with better safeguards than the last one.